So we're going to begin somewhere around the top of page 319, which is drawing Lewis structures for molecules 101. This is different than what you did in grade 10. Grade 10, I don't even know that there was any kind of detailed discussion at all of how to draw Lewis structures. It was just assumed that you knew what they were. Drawing Lewis structures isn't really an end in itself. It's a means to an end. And the end that it is a means to is, if you can draw a Lewis structure correctly, that two-dimensional diagram of dots and lines and symbols can pretty accurately, without the need for complicated bonding theories, allow you to predict the three-dimensional shape of the thing you've drawn with dots and lines and symbols. And from shape, we infer behavior. As a matter of fact, the title of the next section is precisely that, the shape and behavior of molecules. So you can look at section 6.4 and 6.5 kind of as A and B, okay? So, drawing Lewis structures. When molecules form, their three-dimensional shapes are governed by the same attractive and repulsive forces that dictate the shapes of, or the way the ions pack in a crystal lattice, okay? We don't normally use Lewis structures to represent these things. We know they pack in an orderly array of cations and anions. It maximizes attraction and minimizes repulsion. Molecules, though, can adopt a more varied type of shape. And to find that, we got to find out what the Lewis structure looks like. If we wanted to go into more complicated bonding theory to predict those shapes, we could. And I'm not really sure why Lionel did it, but he included the AP version of bonding theory in this book. Maybe he's hoping people will get to it, but when we wrote the AP books, we went beyond just Lewis structures to do it. So if you look in section 6.5, on the bottom of page 345, if you draw a line right here, that's where the regular curriculum is. Valence bond theory, hybrid orbitals, sigma and pi bonds, that's AP chemistry. It's not really that hard, it's just more of it, and we're certainly not going to have time to do it. But the interesting thing is, even without using theories like that, and there's other theories, there's molecular orbital theory, there's crystal field theory, those actually don't get you to really too many different places than what we're going to do does, which is kind of the beauty of Lewis diagram, okay? So, when molecules form, the three-dimensional shapes are also governed by the attractive and repulsive forces that exist within them. The first step toward visualizing the three-dimensional shape of a molecule is to convert its molecular formula into a two-dimensional Lewis structure. That's the reason we do it. One of the simplest examples of a Lewis structure is a diatomic halogen molecule. Obviously, if we've only got two atoms stuck together, the shape of that thing has to be linear. So, but we're just going to start simple, chlorine. So here we have a correctly drawn Lewis structure for a chlorine molecule. The single line between the atoms represents the pair of electrons that constitute that single covalent bond, okay? The reason we draw it as a line as opposed to two dots, some textbooks would draw it like this as opposed to the line. The reason we draw it as a line is for a couple reasons. Number one, bonding electrons behave differently than non-bonding, or what we call lone pair electrons. Electrons that are in a bond are attracted between two nuclei. As a result, they're held more tightly. They take up less space, and if they take up less space, they exert less repulsive force. Electrons that are only attracted by one nucleus are spread out more. They're more diffuse. They exert more repulsive influence. And when we end up predicting the shapes of molecules, it's going to matter whether the electrons that we're talking about are lone pair or non-bonded electrons or bonded electrons. And another reason is it's a lot easier to see how many bonds each atom in a molecule are involved in. If all you're doing is a whole bunch of atoms with a whole bunch of dots, sometimes it's very difficult to manage what are bonding, what aren't, if the number of bonds formed are what we should expect. And also it makes it difficult to count electrons, because we're going to have to do that. The other pairs of electrons that aren't bonding are referred to as either non-bonding or lone pairs. Something we should note right off the bat, notice that all 14 valence electrons possessed by each of those two chlorine atoms is accounted for in a Lewis structure. That's why the first thing you do before you draw a Lewis structure is find out how many valence electrons are there, and then the last thing you do is confirm that what you had is what's on there. Okay? You have to account for all of them. As with any new procedure, just like when we were doing stoichiometry for the first time or limiting reactants for the first time, we employed a series of steps. And initially, the steps for stoichiometry might have seemed a bit onerous and complicated, but after you did it a few times, it wasn't hard at all. Same with limiting reactants. So we're gonna begin to look at those steps now, and we're gonna pick a simple example. Let's begin with a simple example, the Lewis structure for a molecule of nitrogen trichloride. That formula makes sense because nitrogen needs 3 electrons, chlorine needs 1, so that's a reasonable formula, NCl3, okay? Step 1, as I said a few minutes ago, determine the total number of valence electrons in the molecule. Remember, the very first part of this section was how many valence electrons do the atoms in the main group elements have. So it's pretty important that you can identify that. Nitrogen's got 5, just like every other group 15 element, and each of chlorines, being a halogen, has 7, just like the number of letters in the word halogen. And there's 3 of them, so we got 26 valence electrons. When we're all done, we got to account for all 26. Note that this is an even number, which will be true for all examples you will see. There are a few cases where odd numbers of electrons exist, but the vast majority of molecules and polyatomic ions present possess even numbers of valence electrons, and all bonding electrons exist in pairs. It's very unstable for a species, whether it be a polyatomic ion or a molecule, to have an odd number of electrons. That means there's one unpaired electron somewhere, and that's very unstable. We call those things free radicals, and they're not stable chemical species. Once you know the number of valence electrons, you go to step 2. And a number of students, at least initially, find this to be the hardest step. Construct the skeleton of the molecule using lines to indicate covalent bonds between the atoms. To generate the most likely skeleton, the following set of guidelines will be of great help. The guidelines are based on numerous empirical observations and really don't contradict anything you already know, and hold true for the vast majority of molecules. They correspond then to what you would expect given the electron configurations and electronegativities of the atoms. They might seem difficult to remember at first, but you're never going to need all of them. And as with any new skill, they're going to become more familiar with practice. So, guidelines for generating the most likely skeleton, which you do before you put any dots anywhere. If the general formula for the compound is of the form AXN, and by the way, the one we're doing is NCl3. That's AXN, okay? then the central atom A, this thing will be the center with the other atoms around it, will be the one with the lower group number, and the lower the group number, the more electrons it needs to be like the nearest noble gas. So nitrogen is group 15, it needs 3 electrons. Chlorine is group 17, it only needs 1. Okay? Which also usually corresponds to the lower electronegativity. Now, not always, because as it turns out, these actually have the same electronegativity. Obviously, if only 2 atoms exist in a molecule, then there's no central atom. So initially, we get the idea here that nitrogen's going to be in the middle, the chlorines are going to be around. Number 2, it doesn't apply to this, but hydrogen atoms form only 1 bond. What that means is, if we have a skeleton, we can never have any more than 1 line coming from a hydrogen. Why does hydrogen only form 1 bond?
It only has 1 electron.
Yeah, it only has 1 electron to share. How much room does it have in the first energy level?
1.
It has room for 1 more electron, then that energy level is filled. So for the same reason helium never forms any bonds, hydrogen only forms 1. Okay? Fluorine atoms also form only 1 bond. For kind of the same reason. Fluorine's 2s2, 2p5. That's 7 electrons in that second energy level. There's only room for 1 more. So this is also telling you, if you ever have any more than 1 line coming from a fluorine, it's wrong. The other halogen atoms usually form only 1 bond. Well, they all need 1 more electron to be like the nearest noble gas. But any halogen underneath fluorine is in has a valence shell and an energy level that can accommodate more than 8 electrons. So chlorine's a 3rd period halogen. We can fit 18 electrons in the 3rd period. So the only halogen that technically cannot have more than 1 bond is fluorine. If a halogen has more than 1 bond, which means there's 2 lines coming from it, then that halogen would have to be a central atom, and it would have to be bonded to smaller halogens or to oxygen. So obviously there is no halogen smaller than fluorine. So if a halogen is going to be a central atom, the first halogen that can be that would be chlorine. And by the way, if we have any more than 1 bond coming from a halogen, then that means that that halogen has what we call an expanded octet, more than 8 electrons on the outside. Which may sound strange, but again, if we're in the 3rd period, we got room for 18 electrons in that energy level. And we'll get to those exceptions soon. Number 4, oxygen atoms normally form 2 bonds. We know that, need 2 electrons. Can an oxygen atom have 3 bonds? Doesn't have room for any more than 8 electrons in the second energy level. Also, oxygen in a molecule, when you're connecting the atoms to each other, oxygen doesn't like to stick to itself. The exception to that is if the name of the thing you're drawing is peroxide. But normally oxygen does not like to stick to itself. You might remember a formula that we've written for acetic acid that might suggest the oxygen does like to stick to itself. So acetic acid is often written like this, which might suggest that these 2 oxygens are stuck to themselves, but they're not. That COOH is characteristic of what we call an organic acid, and that OOH is really this. Okay? So oxygen isn't stuck to itself, but that is often written like that in molecular form. Okay? And if we have time to get into organic chemistry, which I hope, you'll see. Notice that B makes sense as well. Nitrogen atom normally forms 3 bonds. Why? It needs 3 electrons. Carbon atom normally forms 4. Why? Because it needs 4. Avoid creating rings or cyclic structures, unless you're told. Very few elements form rings. Sulfur does to some extent. Sulfur, element of sulfur is S8, it's solid, and it's 8 sulfur atoms in a ring. We call it crown sulfur. It comes from the side, it looks like a little crown. The only other element that forms rings is carbon. So in organic chemistry, rings are common. Okay? They're not rare at all. Carbon's kind of unique in the chemistry world. It can form chains of any length, it can form rings of any size, and no other element does that, which is one of the reasons that organic chemistry has so many different possible arrangements of it. Okay? So if we look at these tips for skeletons, or hints, using the above rules, we can see that a central atom exists because the form is of the form AXN, and that nitrogen is most likely that central atom. We can therefore sketch the molecular skeleton of NCl3, right here. Now it doesn't matter where the 3 chlorines go. You could put 2 here and 1 here, or you could put 2 here and 1 up here, or you could put 2 here and 1 there. You could even arrange them equilaterally in a triangle, it doesn't matter. Don't try to make the thing look 3-dimensional. Okay? We're going to use the structure that we end up with to predict 3 dimensions, but the structure doesn't need to represent that. The relative orientation then of each chlorine atoms is really irrelevant, because Lewis structures do not depict the shape or 3-dimensional geometry. All that matters at this stage is that nitrogen is in the middle and each chlorine atom is a peripheral or surrounding atom. Step 3. Subtract the number of valence electrons used to construct the skeleton from the total number available. Remember, you have 26. And if you look at the skeleton, we've used 3 lines. Given that each line represents a pair of bonded electrons, we've used 6 to construct the skeleton. Subtract that number from the number available. So we had 26, we've used 6, we have 20 left. And remember, when all is said and done, you got to account for all 26. 6 of them are already accounted for. The next step, assume that all of the atoms in the molecule obey the octet rule, obviously except for hydrogen. Determine, based on that, the number of additional valence electrons required, beyond those already present, to give all of those atoms that required 8 valence electron number. So, how many electrons does that chlorine need, given the fact that it's right now associated with 2? 6. That needs 6 as well, as does that, right? How many does the nitrogen need? 2, because it's already associated with 6. So 6 times 3 is 18, plus 2 is 20. Compare the number of valence electrons available from step 3, which is 20, to the number needed in step 4. If those 2 numbers match, pair up the electrons, and beginning with the peripheral atoms and ending with the central atom. You never start with the central atom. You always start on the outside first, because if there's anything in the molecule or polyatomic ion that is going to violate the octet rule, it'll never be the atoms on the outside. It'll only be, except for hydrogen, it'll only be the central atom. Begin with the peripheral atoms and end with the central atom, placing those electron pairs where they're needed to satisfy the octets. So, and don't just go 1, 2, 3, 4, 5, 6. Pair them up. Electrons do really pair up. It's very stable in terms of a quantum mechanical perspective, and it makes it a lot easier to count them. So there's 3 pairs on the chlorine, 3 pairs on that chlorine, 3 pairs on that chlorine. That's 18. We need 20. The final pair goes there. Okay? In this case, the 2 numbers do indeed match, and so the resulting Lewis structure is shown in figure 645. So we're done. Now the final step, let's look at the final step before we consider the following. You want to count all the electrons in that structure to make sure it matches what you started with. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. One of the ways to make sure that the thing is correct, do the number of electrons in the structure match the number available? Yes. A couple other questions. This may seem an odd question to ask, but are the number of atoms of each element in the diagram the same as the number of each of the atoms in the formula? Yes, NCl3. That may seem like a silly thing to ask yourself, but a number of students, no matter what the formula is, they try to get it to be with one of each, which is silly. So does the number of valence electrons available match the number in the structure? Yes. Does the number of atoms of each element might match the same of each element in the formula? Yes. Are all of the electrons in the structure paired? Yes. And does every atom in the structure obey the octet rule? In this case, yes. If the answer to all of those is yes, it's probably correct. Occasionally though, we have a situation where one of the atoms in the structure either doesn't have enough electrons or has too many. If that's the case, if we've got an exception to the octet rule, it will only be a central atom. Criteria governing the octet rule. A peripheral or surrounding atom must not violate the octet rule. That's why you always start by satisfying your octets first. If an atom does violate the octet rule, then it must be a central atom. That's why you always do the central atom last. This doesn't apply to hydrogen, obviously, but hydrogen can't be a central atom. So when you do have exceptions, exception number 1, atoms belonging to the second period in the table will never have expanded octets. Why? Because there's no room for more than 8 electrons. An expanded octet, more than 8 valence electrons, is only possible for elements belonging to the third period or higher, because only those atoms have access to d orbital electrons. So remember we said the number of electrons that can exist in each energy level is 2n squared. 2 in the first, 8 in the second, 18 in the third, because we have that 3d. Unless we have d orbitals available, which doesn't start till the third energy level, third period, we can't have expanded octets. Exception number 2, sometimes atoms will have fewer than. The atoms beryllium, boron, and aluminum will often have incomplete octets, such that only 2 or 3 pairs of valence electrons will be associated with these central atoms. For example, beryllium only has 2 valence electrons. Yes, it's a group 2 metal, but let's consider, for example, well, what's the electronegativity of beryllium? Look in your book. 3?
1.5.
1.5. What's the electronegativity of hydrogen?
2.1.
2.1. So if we formed a bond between beryllium and hydrogen, the difference would be 0.6, right? Which means it's polar covalent. So if you were going to draw the Lewis structure for this, how many valence electrons do we have in BeH2? How many valence electrons does beryllium have? 2. How many does hydrogen have? So how many valence electrons do we have here? 4. There's only one way we can draw this skeleton. Hydrogen can only have one bond. So the only way we can draw this skeleton is this. How many electrons have we used to construct the skeleton? 4. How many do we have? 4. We're done. Neither atom has an octet. Obviously hydrogen can't, but beryllium's only associated with 4. It's shared every valence electron it owns. It's never going to deal with core electrons. All it has is 4. So it can't get an octet. But notice it's the central atom. What about boron? What's boron's electronegativity? 2. What's hydrogen's? What's that difference? 0.1. So this isn't a polar covalent series of polar covalent bonds. These are pure covalent because the difference is only 0.1. How many valence electrons do we have here? Boron has 6. We got 6, right? The only skeleton we can draw, I'll make it an equilateral triangle, but you wouldn't have to. The only possible skeleton is that, right? Hydrogen can't ever have more than one line. How many valence electrons have we used to construct the skeleton? 1. Hydrogen's fine, it's got the electron configuration of the nearest known gas helium. That's what happens when he has one bond. But boron's only got 6. What about aluminum and chlorine? What's aluminum's electronegativity? 5. Chlorine's is 3, right? So, what's the electronegativity difference? 1.5, right? That's polar covalent. So technically, that's a molecule too. If we drew that skeleton, which is the only skeleton we can draw for that, we would see that once again, aluminum has an incomplete octet. Now, we're going to have other dots around it. Matter of fact, while we're here, let's do it. How many valence electrons do we have in that structure? Aluminum's got 3, right? Chlorine is how many?
7.
It's a halogen. So 7 times 3 is 21, plus 3 is 24, right? There's the skeleton. So we've used, of those 24, we've used how many? 6. So we've got 18 left, right? Each chlorine needs 6. Aluminum needs 2, but we don't have that many. When we satisfy the octets of the peripheral atoms, all 18 of those electrons that we have left are done. Chlorine's fine, but aluminum has an incomplete octet. In other words, it's shared every electron it owns, and it still can't get an octet. Now, we're also going to look at scenarios where we have an expanded octet on the central atom. That's actually a pretty straightforward process too, okay? Step 6, which is probably something I should have put in before the exceptions. If the numbers in step 5 above agree, then as a final step, check that the total number of valence electrons represented in the diagram matches the total number of valence. In this example, the number of valence electrons matches. So that was about as simple an example as you're going to get in terms of predicting, in terms of doing Lewis structures. If you were then going to try to predict the shape of NCl3, you would look at the central atom and look at how many atoms are bonded around it, and are there any lone pairs on that central atom. And as we're going to see in section 6.5, that'll allow us to put it in a category that predicts its shape very accurately. But we're not there yet, okay? Look at number 2 in the code check. Hydrogen sulfide is a potent, foul-smelling flammable gas. You can detect hydrogen sulfide in concentrations in the parts per billion. That's how sensitive your olfactory organs are for that thing. Why is the molecular skeleton SHH incorrect?
Because hydrogens can't be bonded together.
Yeah, hydrogen can't ever have 2 lines. Hydrogen can't be a central atom. Okay. So the most likely skeleton is sulfur in the middle, because sulfur needs 2 electrons. It forms 2 bonds, just like oxygen. Determine the total number of valence electrons present in each of the following molecules. I'm sure you guys can do that quite easily. Hydrogen has 1, and there's 2 hydrogens. Selenium is right underneath sulfur. So selenium has 6, sulfur has 2, so that's, selenium has 6, each hydrogen has 1, so that's 2, so that's 8. What about carbon tetrachloride? What's the total number of valence electrons there? NF3 is the same as NCl3 because fluorine's a halogen just like chlorine. So that would be 26, right? 7 times 3 plus 5. PCl5, what about that one? That may look weird because phosphorus is in nitrogen's group. NF3, but, or NCl3, but PCl5. That must mean that phosphorus has 5 bonds. Can it have 5 bonds? That's an expanded octet, isn't it? 10. Is that possible for phosphorus? Couldn't be possible for nitrogen, because nitrogen's a second period element. And phosphorus is in the third period. So it is possible for phosphorus. And we're going to talk about expanded octets soon. But in any event, how many valence electrons are there? 5 times 7 is 35, plus 5 is 40. Again, an even number. Look at SF6, that's also got to be an expanded octet. Sulfur's a third period element. So 7 times 6 is 42, plus 6, 48. So there's a whole bunch of electrons there. Okay. Sample problem, this is equally as easy as NCl. Draw Lewis structure for molecule 1. You got 8 valence electrons left. This is the only possible skeleton. For the same reason, S would be in the middle of H2S. Oxygen is in the middle of H2O. Electrons available. We've used 4. We've got 8, so 8 minus 4 is 4. Hydrogen doesn't need any. But the central oxygen needs 4. So here's the structure. Now we draw it straight, but in 3 dimensions, water actually isn't straight. It's a bent or V-shaped molecule. And it's a good thing it is. If it wasn't, you and I wouldn't live. No life anywhere would live if water was a straight molecule. Okay. Construct the Lewis structure for a molecule of carbon tetrachloride, ammonia, BCl3. Well, let's look at number 1. BCl3 would be the same as H3. This is on the board just a second time. If I wanted you to draw this, it would just be like this. Notice that boron, once again, has an incomplete octet. And you wouldn't even have to make it an equilateral triangle, as it turns out it is, but any arrangement of those 3 chlorines around the boron would be just fine. But let's do number 1. Why don't you guys do number 1? Follow the steps. You're not going to have any exceptions here, so you don't have to worry about that. Not a lot of room there, but electrons, carbon's got 4, each chlorine's got 7, so 28 plus 4 is 32. Let's make sure that all 32 are there. 2, 4, 6, 8 times 4 is 32. Carbon can't have an expanded octet, nor can it have an incomplete octet. Now notice that carbon satisfies its octet here by 4 single bonds. Carbon can also satisfy its octet by a double and 2 single bonds, or a triple and a single, or 2 doubles. And I think that's kind of one of the unique features of carbon. It'll get 4 electrons any possible way. Now, if that represented carbon tetrachloride in the real world, then it would be a flat molecule, wouldn't it? And if this was the molecule, then we would expect each of those bond angles to be 90 degrees. But as it turns out, again, each of those pairs of electrons are regions of negative charge. They want to try to get out of each other's way in 3 dimensions, right? So in 2 dimensions, they're only 90 degrees apart. But in the 3-dimensional world, they adopt what's called a tetrahedron, where they can get farther than 90. They're actually 109.5 degrees. And what that looks like is something a little more like this. Arguably a rather low-tech bottle kit. Accurate nonetheless. So let's say that at the end of each of these yellow sticks, we had a chlorine atom. That's the shape it's going to adopt in 3 dimensions. Okay. We call that a regular tetrahedron. And those bond angles are more than 90. So that's what a 2-dimensional diagram means in a 3-dimensional world. You can get pretty much the same thing. If you blew up 4 balloons and taped them together where you tied them, if you press them down on a table, they're going to sit flat. But if you flick them with your finger, they're going to do this. Now you think, well, it can't be that simple. It is. What I have just done is apply a principle of taking a Lewis structure and predicting the 3-dimensional shape called valence shell electron pair repulsion theory, affectionately known as Vesper theory. And it's based on a very simple premise. Electrons are regions of negative charge. They want to get out of each other's way. So all of the shapes that we're going to talk about in section 6.5 are based on that. The farthest away those electron groups can get from each other is a shape that is dictated like that. If we had 3 instead of 4, the shape would be different. If we had 5 instead of 4, the shape would be different. If we had 6, it would be different. So for example, SF6 is a different shape than PCl5. PCl5 is different than NCl3. H2O is different than carbon tetrachloride. But as long as they fit into these categories, we can really accurately predict the shapes. And if you look briefly ahead to section 6.5, if we blew up 2, 3, 4, 5, and 6 balloons and tied them all together, and then flicked them with our finger, the shapes they would adopt are on the bottom of page 331. And there are names for each of those shapes. Bottom of page 331. The one on the left is just linear. The second from the left is called triangular planar. The one next to it is that one. That's called tetrahedral. The second from the right is called trigonal bipyramidal. And the one on the right is called octahedral. And it doesn't matter what the atoms are. All that matters is how many of the electrons there are in those bonds around the central atom. And the shapes will always be the same. And there's nothing easier than Vesper theory. We could do, if we had time, or if we had the inclination, or if this was an AP course, valence bond theory. molecular orbital theory, crystal field theory, we could do all that, but we wouldn't get to any different results. So that's why Lewis structures and Vesper theory is so easy. If we'd have done ammonia, NH3, we would have gotten, using exactly the same steps, we would have gotten this. And notice how similar that is to this. That was done in the book. As it turns out, the shape of that thing and the shape of this thing are the same. What's around the central atom doesn't really matter. All that matters is what's around. The peripheral atoms don't matter. All that matters is really the central atom. So notice that central atom has 3 atoms stuck to the central atom and a lone pair. This has 3 atoms stuck to the central atom and a lone pair. So the shape of that is going to be pretty much the shape of that. As it turns out, it's called a trigonal pyramid. We're going to get to that. I'm getting ahead of ourselves here. What about multiple bonds? So this is a kind of a little more of a complicated feature rather than just single bonds where all the numbers agree. Let's look at some multiple bonds. We've seen that one pair of valence electrons shared between 2 adjacent nuclei constitutes a single covalent bond. There's also many cases where the covalent bonds between 2 atoms involve more than one pair. These are known as multiple bonds. If 2 pairs of electrons are shared between 2 atoms, the bond is called a double bond. And yeah, you guessed it, if 3 pairs exist, a triple bond exists. I'm not aware of a quadruple bond. As you might expect, as multiple bonds involve more attractive forces between 2 atoms, like as opposed to one pair of electrons between 2 positive nuclei, if we got 2 pairs of electrons, we would expect that bond to be stronger. We would also expect it to be a little shorter. Because multiple bonds involve more attractive forces between 2 atoms than single bonds do, multiple bonds are stronger. Bond strengths are usually measured by the amount of energy required to break a mole of them, and are thus represented by kilojoules per mole. The greater attraction between the atoms in a multiple bond also draws those bonding atoms closer together. And we can very carefully measure the strength and the length of those bonds. This means that multiple bonds are also shorter. Table 642 compares some single and multiple bond strengths and lengths. Remember, a picometer is 10 to the minus 12 meters. So, a carbon-carbon single bond, 347 kilojoules per mole, 154 picometers. Double bond, stronger and shorter. A triple bond, stronger and shorter. But notice with carbon, is a double bond twice as strong as a single bond for carbon? No. Is a triple bond 3 times as strong as a single bond? No. And then you look at nitrogen. A nitrogen-nitrogen double bond is more than twice as strong as a single bond. And a triple bond is way more than 3 times stronger than a single bond. What's going on there? Well, what do you know about the size of nitrogen and carbon? Which is smaller? Nitrogen takes up a little less space, so it's easier for those nitrogen atoms to get closer together. So there's 2 things going on when multiple bonds form. We've got more attractive forces, which tends to bring the atoms together, but we also have electron-electron repulsion. And if the atoms aren't that small initially, then they're not as easy to get close together, and the electron-electron repulsion affects both the length and the strength of the bond. A nitrogen-nitrogen triple bond is among the strongest elemental bond known. certainly in terms of diatomic molecules. And that's why when we breathe air in, one of the reasons when we breathe air in, 70% of what we're breathing in is nitrogen, N2. Only 21, 22% is oxygen. We can't do anything with the nitrogen. The bond is way too strong. We need nitrogen for proteins and for nucleic acids and enzymes and stuff. We just can't get it from the air. There are organisms that can break that bond. Any of you in bio-11? Have you talked about at all rhizobium bacteria? Nitrifying bacteria? No? Well, there's two ways that we can get nitrogen from the atmosphere. Nitrifying bacteria that do it, that they have an enzyme and they break it all by themselves. Or lightning. Volcanoes too. But we can't just do it by breathing the nitrogen in. Anyway, I digress. And carbon, single, double, and triple, and nitrogen, single, double, and triple, those are the same element, but here's two different elements. Carbon, oxygen, single, carbon, oxygen, double, carbon, oxygen, triple. Okay. Let's follow the steps outlined above to draw the Lewis structure for a molecule that contains double bonds. For example, carbon dioxide. And even if we didn't know it contained double bonds, we're going to find out that it does when we draw the Lewis structure. So carbon dioxide suggests that formula. So we're just going to follow the steps. How many valence electrons do we have? It's in the book, you guys. 4 plus 12 is 16, right? So we got 16 valence electrons. Next step, draw the skeleton. Carbon needs more electrons than oxygen does. Carbon is probably the central atom given that formula. So the most likely skeleton is that. Okay? Keep going. To use that, to draw that skeleton, we've used 4.
And 12 more.
We've got 16, so there's 12 left. But how many do we need? Each oxygen needs 6, right? Carbon needs 4. So we need 16, we only got 12. And nothing in this combination can violate the octet rule. So notice that 16 electrons are required, but only 12 electrons are available. Does everybody see why we had 16, we've used 4, we've only got 12 left? Does everybody see why we need 16? This needs 6, that needs 6, this needs 4, right? It's already associated with 4, it needs 4 more. This is associated with 2, it needs 6 more. So 16 needed, but only 12 left, so we're 4 short. We are therefore lacking 4 electrons. This means that we must return to step 2 and redraw the skeleton such that we incorporate one multiple bond for each pair of electrons we're short. In other words, for every multiple bond we build into the skeleton, we get 2 closer to having what we need match what we have, okay? And we'll prove that. Let's redraw the skeleton. Let's put a double bond there. Now remember we had 16 available, right? 6 times 2 is 12 plus 4 is 16. We've drawn 3 lines here. So we've used 6, we've got 10 left. Remember originally, with 2 single bonds, we were 4 short. If we put a double bond here, 10 left, how many do we need? Well, this oxygen only needs 4 now. This carbon only needs 2, that's 6. This oxygen needs 6. So right now, 10 left, but 12 needed. So notice now, after we put 1 double bond in there, we're only 2 short. Now the next choice is, where do we put the next bond? Do we put 1 here, or do we put 1 here? Both of them give carbon the octet it needs, and both of them, whether we put 3 here and 1 here, we've used 8. So regardless of which approach we adopt, the numbers work out. So to construct that skeleton, we've used 8. We've got 8 left. How many do we need? Well, this oxygen needs 2. Carbon doesn't need any, it's got 8, 2, 4, 6, 8. This oxygen needs 6. So 8 left, 8 needed, right? Or, let's say our skeleton was this. Same thing. 8 used, 8 left, how many do we need? Carbon doesn't need any, this needs 4, that needs 4. So both of the skeletons have the numbers agreed. Because we are 4 electrons short, we can consider either of the following modified skeletons. Although both skeletons above show carbon forming a total of 4 bonds. As oxygen normally forms 2, remember that was one of the guidelines for skeletons? We would choose skeleton 2. Because skeleton 1. Skeleton 2 shows neither oxygen having 2 bonds. Skeleton 1 shows both oxygens with 2 bonds. Now, this is true, but it's not a reason, a good enough reason. Molecules often possess a high degree of symmetry, and that also makes this choice more likely. That's true enough, but that's not really enough. And there is another way of proving that this is the right skeleton. Number 1, you look at the data. If this was the right skeleton, then we would expect that one of those bonds would be stronger and shorter than the other one, right? Now we have data to support that. We can look, we know about the strength of carbon, oxygen, single, double, and triple. So the proof is in the data. If we look at carbon dioxide, we find that both bonds have the right length and strength of a double bond. We don't see a carbon-oxygen triple, nor do we see a carbon-oxygen double. But even without the data, there is another way to assess which of these things is correct. This isn't really enough. The way to do it is called determining formal charge. Now that's a little beyond grade 11. I wanted to put formal charge in here, but you may say, well, that's too complicated. It's not complicated at all. Luckily, they threw it in the sort of the AP stuff they left in, and I'm pretty sure it's still in here. So we did it for the AP, and I think it's yes, bottom of page 351. That's where we put it. Now, am I going to ask you to do formal charge? No. But if you wanted to prove to yourself why it's this one and not this one, you use formal charge. Formal charge is an entirely fictitious charge that is used to defend the most probable Lewis structure of a molecule when several different structure arrangements are possible. So I wrote this and I wanted to put it in right here, underneath this, and make sure that would be too difficult. Sherry and I kind of said, no, we should, but whatever. So anyway, I think Meg finally said, well, it's not part of the basic curriculum anyway. No, we know, but anyway, it's so easy. Formal charge in an atom in a molecule is the charge each atom would have if all bonding electrons were shared equally between the bonded atoms. There are a couple of ways to calculate formal charge. Formal charge of an atom equals the number of valence electrons the atom owns minus the number of valence, minus the number of lone electrons and number of bonding electron pairs. So effectively what you do to calculate formal charge is you look at the formal charge an atom owns by itself, and then you look at the number of electrons you've given it in the skeleton. And you do that for both of the possible skeletons. Ideally, you want a formal charge on an atom to be 0, because the number of valence electrons an atom owns compared to the number of atoms you've given it in a structure. So for example, if we look at this one, let's assume that each of these, let's draw them like this, okay? So in a bond, we assign each atom in a bond half of the electrons in the bond, okay? So, if we drew all the electrons in for that skeleton, let's see how many valence electrons each atom would be assigned in this structure. Each bond, each atom in the bond is given half of the valence electrons we've given it in the diagram. So, carbon, we're going to give carbon one of those two there, see that? And one of those two. Over here, we're going to give carbon one of those two and one of those two. So how many valence electrons is associated with carbon in this diagram?
4.
4. How many does it own?
4.
4. So what's the formal charge on carbon? 0. It owns 4, we've given it 4. That's ideal, okay? Let's do the same for oxygen. Each oxygen, in terms of the bonded electrons, we're going to give it half of those. So the valence electrons that oxygen owns is 6, right? We've given it how many?
2.
Well, hang on. How many does it have here? 8. Now, 8 minus 6 is negative 2, right? Which of these two atoms has the greater electronegativity? Oxygen's 3.5, carbon's
2.5.
2.5. So if oxygen has a negative formal charge, then it would make sense that because it's the more electronegative atom, it would have a formal charge of negative 2, right? Same with this. So let's keep going. While not particularly scientific sounding, this is a very easy way to calculate formal charge. Formal charges are generally shown next to each atom in a molecule with a circle drawn around it. You don't have to worry about that. It's important to remember that formal charges are not actual charges. They do not produce electronegativity or polarity in a molecule. They simply assist us in determining which is the most likely structure. So, the following general rules apply to formal charges. The sum of formal charges in a neutral molecule is equal to 0. Now, this is a neutral molecule, so we should expect that. The sum of all formal charges in an ion is equal to the ion's charge. Small or 0 formal charges on atoms are preferred. So that's ideally the case. For structures with atoms with non-zero formal charge, the preferred structure will be the one with the negative charge on the most electronegative atom. So right now, in this structure, the negative formal charges are on the most electronegative atom, right? Each of the oxygens. Let's look at, look at the practice problem on the top of page 353. Assign formal charges to each atom in each of the following 2 structures for carbon dioxide. Predict which structure is favored. Now, when we worked out carbon here, it had there were 4 electrons that are known as an atom. This was the least of the 2 electronegative atoms. The oxygen was the negative, right? Does that follow the rules? So, compare that to B. If we look at the sample problem, we can do it. The sample problem tells us the actual steps. Hydrocyanic acid is produced by bubbling gas, blah, 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 blah. There's 2 possibilities for the skeletons. 2 possible structures with the triple bond between carbon and nitrogen and the assigned formal charge to all atoms. Which structure is preferred based on minimizing formal charge? So we've got carbon as the central atom or nitrogen as the central atom. So don't worry about the resonance. Calculate formal charges using formula. Dots plus dashes for each electron in the first structure. So each dash, remember, is 2 electrons, so we're going to give each element with a line connected to it 1 electron, half of those. So for hydrogen, what's the formal charge? 1 is how many valence electrons it has, plus 1, which is 0. Carbon, 4 valence electrons, plus 4, which is 0. Nitrogen, 5 valence electrons, minus 2 plus 3. Why 2 plus 3? Because it's got a lone pair on the right, and we're going to give it 3 of the lines, right? So nitrogen is 0. So all of the atoms in the structure on the left have a 0 formal charge. If we look on the right, the hydrogen's the same, 0. Nitrogen has 5 valence electrons as an atom, but we're subtracting from that how many we've given it in the structure. We've given it 4. You see 1 line on the left, 3 lines on the right? So nitrogen has a formal charge of 1 plus 1. Not minus 1, plus 1, and not 0. Carbon has 4 valence electrons as an atom. How many have we given it here? 5. So it's got a negative charge. The first structure with the central atom is preferred because no atom has a formal charge. Make sense? So if we do it to carbon dioxide, okay? Each oxygen, actually, that's my mistake. There's too many electrons there. There it is. So what would be the formal charge on this oxygen? It's got a 6 valence electrons. There's the double bond. 2, 4, 5, 6. 0. One, 2, 3, 4, 5, 6. 0. Carbon, 4 minus 4 is 0. Right? But look at the one on the right. What would be the formal charge of the oxygen on the left of that diagram? This is B on the top of page 353. Oxygen has 6 valence electrons, right? Agreed? We're subtracting from that how many electrons we've given it in the structure. How many have we given it in the structure? 7. So that oxygen has a formal charge of -1. In the other diagram, they're both 0. What about the oxygen on the right? What's its formal charge? 6 minus what? 6 minus 5, which is positive. Well, oxygen should not ever have a positive electronegativity when connected to something that's less electronegative than it is. What about the central carbon? Central carbon's fine. 4 minus 4 is 0. But because each oxygen has not only a non-zero formal charge, but a different formal charge than the other oxygen, we wouldn't pick the one on the left. Now, will I make you do that on a test? No. But it's not just the symmetry that makes this thing work, okay? There's, if you remember the guidelines for the skeletons, why does oxygen like to form 2 bonds? Well, you expect it to want to form two because of the nearest noble gas limitation. So it would be weird if it formed three. Are there any situations where oxygen does form three? Yeah. And that's carbon monoxide. That's tricky. Let's just make sure that this is the right structure before we move on. To construct the skeleton, we've used 8. We've got 8 left. Carbon doesn't need any. This needs 4, that needs 4. So again, we would normally put the dots like that. Okay. What about carbon monoxide? What about that one? That's trickier. You all know that that's a thing, right? Carbon monoxide? Do you know why it kills you, by the way? You know that it does kill you, right?
Yeah.
Okay, let's draw the structure and then I'll quickly go into it in like 2 minutes. How many valence electrons do we have? Let me draw it in 2 different colors because it's going to make this easier to understand. How many valence electrons?
10.
Well, carbon's got 4, oxygen got 6, so isn't that
10.
10? And it's even, so you're there. So let's draw the skeleton. Not hard to draw the skeleton, at least first. But instead of drawing it with a line, let's draw a single bond like this. Okay? We're going to put a single bond there. Okay? And we'll make oxygen red. So to construct that skeleton, how many of the 10 have we used? 2. So we got 8 left. How many do we need? Well, carbon's associated with 2. How many more does it need?
6.
So we need 12, right? Nothing here can have an expanded octet. So we need 12, which means 2 multiple bonds. So let's draw the 2 multiple bonds in. Let's first put a double bond in there. And let's agree that we're not there yet. To construct that, we've used 4. So we've got 6 left. How many do we need?
8.
That needs 6, that needs 6. So we need 12, we only got 10. So we got to put another multiple bond in. How many valence electrons does carbon have? In total? 4. How many electrons does oxygen have? 6, right? So the third double bond cannot be this. Or this third multiple bond, it can't be there. Because that would leave carbon with only 1 more electron. When we draw 3 lines in, my point is this, when we draw 3 lines in, everything works fine in terms of agreement. We've got 6, we got 4 left. Where do the 4 go? 2 there, 2 here. Fine. The problem is that this, one of these triple bonds is an unusual bond. And chemists have a name for it. It's called coordinate covalent bond. And if you break down the lines into the electrons that has to be in them, you see what's going on. So there's 1 bond. There's the second bond. But the third bond can't have a black dot because carbon, 2 of its valence electrons are here, the other 2 are here. So the third bond is this. It's called the coordinate covalent bond. Basically, it's proof that it's so important for an atom to be like a noble gas that even if it has to use 2 of its valence electrons for 1 bond, it'll still do it. Okay? It's like going into business for with somebody else and the other person has only 1/3 of the money, and you got 2/3 of the money, but you still need it because without them you can't start the business. So 4 of those 6 electrons are supplied by the same atom. If you want, Google why carbon monoxide kills you. It kills you